delighted to welcome Dr. Tony Jebara. Tony is the Director of Machine Learning Research at Netflix, and he will be discussing how to personalize AI. Please welcome Tony to the stage.
Okay, great. Thank you for inviting me to this event, and thank you, everyone, for coming to my session. Today, I'll be talking about 3 vignettes of how we use machine learning and AI at Netflix to personalize the experience. And what we like to think of at Netflix is we don't have one product. We actually have over 100 million products because each user gets their own personalized experience. So this is an example of one user and their homepage. It looks specially curated for them. And what we're seeing here is a machine learning algorithm personalizing the ranking of all the movies and the TV shows just for them. Also laying out the page so that it looks nice and clustered into meaningful rows. We also have personalized promotion. What would be a good billboard to advertise to this user? And even the imagery you see here, the image representing that movie or that TV show has been selected also in a personalized way for the user. We also look at other ways of personalizing, even the way we message our users and we send them emails or push notifications of what's coming up next or new movies that are being released and new TV shows. And we also personalize things like even the content we're going to acquire in the future. So how do we do this? I'll talk about 3 systems, 3 vignettes. The first one is, how do we predict what you will like? And this is a technique called collaborative ranking. The basic idea is we've got over tens of thousands of movies and TV shows. Now, for every user, what are the top 20 or the top 30 TV shows and movies for them? Because no one has time to sit there and browse tens of thousands of possibilities when they come home from work and they want to watch something interesting at the end of the day. We started this type of effort in 2006 with this thing we call the Netflix Challenge. And the idea there is to look at this big matrix of users and movies and see how the users rate the movies and say, do they give them 1 star, 3 stars, 4.5 stars? But we moved away from star ratings because it turns out stars are kind of aspirational. People give a lot of stars to fancy movies and TV shows. For example, an Oscar-winning title like Citizen Kane is going to get 5 stars, but no one really wants to watch Citizen Kane. So we moved away from stars, and now we look at the actual engagement and plays the users are generating. And we say, OK, these are the 3 users. These are 3 movies. Here are the users that actually played those movies. And then we can say, let's look at one user. And from that user's play history of the things they engaged with and watched, what can we suggest for them next? So an old way of doing this, which got really kick-started in the 2006 challenge, was to take this big matrix of ratings or plays called R and to break it up and rewrite it as a product of 2 skinny matrices. That helps summarize the user and brings them down to kind of a lower dimensional summary describing their taste profile. So we moved away from linear factorization, and now we live in a deep learning world where we go through nonlinear types of machine learning. And so this is an example where we go through the viewing history of the user and we compress it in multiple stages rather than in one matrix stage, and going through sigmoid squashing functions, and then are able to reconstruct it also through multiple neural layers. And so this is like the nonlinear version of the matrix factorization, and that works better. What we're trying to do here is take your view history, and in just a few numbers, maybe 20 or 30 dimensions in the middle, summarize everything about your view history. There's going to be some inaccuracies in that summary. But then when we re-explode back and reconstruct your view history, we're going to get some suggestions of some new movies you may want to watch next. And so you don't want perfect reconstruction. You want a coarse reconstruction because it suggests new movies that had zeros on the input. Now they get slightly larger than zeros. You can also make this technique probabilistic and move away from standard neural nets into techniques called variational autoencoders or probabilistic neural networks. And the idea there is you don't really want to just predict here's what the user's reconstructed view history should be like. We want to predict a distribution over all the possible things you might be interested in the future, because there isn't just one path into the future of the things you're going to do next. So probabilistic nonlinear factorization. And then also the final kind of last modification is to make sure when you make a prediction, it's like multinomial prediction. And that means put probabilities on all the movies so that nothing can have negative probability and all the probabilities sum to 1, right? The person's going to watch something. There's a probability over every possible next play. It should sum to 1, and you can't have negative probabilities. So that's one last kind of fix. And then what you have is the deep, nonlinear, probabilistic version of recommendation. And so on standard benchmark tests, this is outperforming classical methods. So the classical methods are in the bottom 3 rows, upstairs and downstairs. Those are kind of matrix factorization and linear techniques like SLIM. And then in the second line in each table is the neural network approach. But then in the first line is the probabilistic neural network approach. And you can see that it has better, let's say, recall and better NDCG, which is a way of saying how good did we rank the user's next plays. So this is where we are now, that we've moved away from linear methods to deep neural methods that are also capturing probabilistic concepts as well. Okay, so that's how we can predict what the user is going to watch next, but it turns out being good at prediction isn't always necessarily the best way to make a recommendation, right? And it's subtle. The reason is predictions are observations and they're correlations. But if you're going to actually make a suggestion in a recommendation engine, you need to think about the causal effect of that suggestion. And so this led us into this new domain called causal learning. And what happens when we intervene and we present something to the user, even if what we predicted was good, turns out sometimes when you suggest something to someone, they'll change behavior just because you suggested it. Maybe what I want to watch next tonight is Narcos, but if it's over-promoted to me, I might actually say, no, I don't want to watch it anymore. So there's these funny things that happen when you intervene. This leads us to the domain of causal learning. And it turns out AI and machine learning are great tools, but they're primarily predictive tools. They're trying to predict, and they're trying to find correlations in the data. But the reality is we need machine learning and AI to take actions in the real world, not just make good predictions. And so we don't want to just learn patterns and correlations. We want to see what would actually happen when I intervene in a causal way. So here's a great example. This is kind of a toy problem. Let's say I'm looking at the price of airline tickets, and I work at an airline company, and I look at the sales of my airline seats over time. What I might notice is sales tend to peak in certain times of the year, like during the holidays. Lots of people fly to see family. And maybe the prices for my airline tickets also go up. And so if I plotted the price and I plotted the sales numbers, I would get this really funny pattern, which is when price increases, sales increase. So should I go and tell my boss, hey, increase prices, sales will just double and we'll sell even more and we'll make tons of money? And it turns out these types of correlations in the data can sometimes be really misleading. You want to think causally, not correlationally. And so it turns out there's a hidden confounder. If X is the price and Y is the demand, it turns out the price doesn't completely determine the demand. There's other factors out there that we don't get to observe, like the fact that it's a holiday or there's some conference I didn't know about in Amsterdam right now, which is increasing demand. So these confounders mean you can't just learn a mapping from X to Y, which is what 99% of machine learning out there does, right? Go from input to output and make sure you get the error as small as possible. That doesn't work if there's hidden confounders like holidays. And so we learned this the hard way when we studied messaging. When we send messages to our users, we're trying to encourage them to watch a show that just got added to Netflix right now, or a new season just got released for one of your favorite shows. We'll send you an email, or we'll send you a push notification to tell you, hey, check this out. You may be interested in this new show. So if you look at the messaging variable X, did I send a message, what kind of message, and you look at the output Y, which is how much the user watches, you're trying to learn the mapping from X to Y. If I send you a text or an email, how many minutes of extra watching does that cause, right? That's a reasonable thing to try to model. But it turns out there's a hidden confounder, You got to think about this, and it's kind of easy to get tricked by it. The time of day people open their messages and check their apps and check their push notifications turns out to be also the time of day when they're most likely to just watch Netflix, right? It's the time when they're awake, they're done with work, and they're doing other things. So there's going to be a natural correlation between checking your messages and watching more, and it's not because the messages made you watch more. It's just because you're doing stuff that's not work and not sleep right now. And so this is called an activity bias, and that's kind of a hidden confounder. So how do we fix the problem? It turns out you introduce a little randomization, Z, which we call an instrumental variable. Z, think of it as some randomization that sometimes stops the messages or sometimes doubles the messages, kind of a little random perturbation to how you do messaging. And then you start to think about the problem causally and say, let me try to predict X from Z. Okay? You learn that with machine learning, and then you reconstruct the X from the Z. And then you do another stage of machine learning which goes from reconstructed X to Y. So don't learn to go directly from X to Y. Learn to go from Z to X, and then from the reconstructed X, go to Y. So you learn 2 stages of machine learning, 2 predictions. And it turns out that captures the causal effect. And it turns out techniques like this have been used to, for example, prove causal effects in kind of science in econometrics. For example, do cigarettes cause cancer, or does having cancer make you more inclined to start smoking? Being predisposed to cancer makes you predisposed to smoke. How do you capture that? It turns out you need some randomization, you need some perturbation, like this Z. And we had that when we added taxes to cigarette smoking in different countries over time, differentially. That randomization wiggles the X, modifies that randomly, and then you can capture the causal relationship. So we looked at the outcome, and it turns out this led us to much better conclusions. So here is the effect on viewing of sending the user emails or push notifications or in-app notifications. Those are 3 possible messaging types we can send to the users to encourage them to watch some new things they may be interested in. So it turns out ordinary regression, which is standard machine learning, gets the effect completely wrong. It tells you sending an email gives you negative effects on viewing. Sending a push notification gives you negative effects on viewing. And sending in-app gives you a slight positive effect. So when you present this to your business partners, they say, that's ridiculous. How can sending an email make someone watch less? How can sending a push notification make someone watch less? And it's because upstairs, we didn't do the 2-stage causal modeling. When you do the 2-stage causal modeling downstairs, you actually see everything has a positive effect, and the biggest driver of extra viewing turns out to be push notifications. So we got completely wrong conclusions when we did traditional machine learning, but when you do the proper causal learning, you start seeing, this is the actual actionable effect. We also personalize the images in our service, and the reason why is this is also explaining to the users why we're doing certain recommendations. Why are you recommending this movie to me? And I'll explain how we do this, but it involves a slight foray into online learning. So standard, again, machine learning classically is you collect a bunch of data, and then you look at a bunch of models, and you say, aha, that's the best model. That's your standard batch machine learning approach. The problem with that is collecting data might take months on many users. And then doing all the learning of the models and the fixing of the models also takes you many months. And then making an engineered system that can actually change things for the users takes you many months. And then you do what's called an A/B test. Half the users get the old experience, and the other half get this new machine learned model that hopefully is better. And if that's better, then we roll it out, and then everybody gets the better machine learned model that gives them a better Netflix experience. The problem with this is there's a lot of regret, right? I was giving people a bad experience for many, many months until I collected all the data I needed. I figured out just that single best model out of all the possible models, and then built something and tested it. That's called batch learning, and it's got a big regret. But through online learning, we can do much better and minimize the regret. So this is one technique called Thompson sampling, and it's used for picking kind of the best action, let's say the best machine to play at a casino. But the idea is you try everything. Try all your light bulbs. Try all your models with a probability. And then you slowly kill off the ones that aren't doing so well until through gradual process of elimination, you find the best machine learning model. So rather than waiting till you get tons of data and then finding the single best model afterwards as a separate batch learning process, you slowly get some data and use it to turn off some of the models until you're left with the best one. What's nice about that is you get much less regret along the way because everyone's getting slightly better and better models as you go through this data set over the next few months. And so this is how we pick the best images to show for our TV shows. So it turns out this is a Netflix original called Unbreakable Kimmy Schmidt. This one is the best image to show for Unbreakable Kimmy Schmidt, and we quickly figured this out rather than doing a bunch of data collection and machine learning to figure out that this is the best winner. But we don't stop there. We actually want to personalize the best image for that show for you. So how do we do that? For instance, here's Good Will Hunting. We also condition the best action or the best image on the user's features, the things they've watched in the past, the types of devices they use, the country they're in, all these other things we can measure about the user. And then automatically we learn that the best image to show for Good Will Hunting, if you watch a lot of romance, is this picture of Matt Damon kind of in a romantic setting versus, and Minnie Driver. Versus if you watch a lot of comedy, the best image to show you for Good Will Hunting is this picture of Robin Williams, who's a comedian. And so what we're trying to say is, here's a recommendation, watch Good Will Hunting. And since you like romance, it contains some interesting romance in the story. Versus if you don't care about romance, oh, there may be some interesting comedic parts with Robin Williams that you could be checking out. Similarly, we can also capture preferences for that user for certain actors. So maybe someone likes Uma Thurman movies, this is the better picture for Pulp Fiction for them. Somebody watches a lot of John Travolta movies, this is the better picture of Pulp Fiction for them. And it turns out, through this improvement, we're getting better accuracy and better engagement with our users. So if you start off in green with a random image showing, you can improve things by finding the single best image for everybody. But then if you do this contextual bandit, which is saying, what's the best action given the context that this user likes to watch this kind of stuff and has this type of features, that gives you an improvement. And so here's a quick video. Sorry. So it turns out we're learning the best images without doing computer vision, just by seeing what's getting engagement from the users through this kind of online learning technique. So to summarize, do machine learning to predict what your users are interested in, but also think about causal learning because you're going to take actions based off of what you've found in the data. And finally, find ways to use machine learning to explain your actions to the users so that they trust the recommendations you're giving them. And we are hiring. If people are interested, please come to the website. Thank you.
Thank you, Tony. That was great to get the behind the scenes at Netflix, and I'm sure a lot of people are sort of going to email you right after. Just a question. So, you know, the more data you have, probably the better the recommendations. And I was wondering, how do you deal with sort of the long tail or the obscure items for your recommendations?
So that's a great question. This is another aspect of being kind of causal rather than correlational in your learning. The long tail tends to get punished when you just do observational kind of machine learning, because if you don't distinguish, why did this person just watch this show? Why did this user watch Narcos today? Is it because they really love that show or because we promoted it and recommended it too aggressively? Turns out the long tail kind of gets hidden away due to lack of promotion and in a way gets suppressed. So you want to be more causal in your machine learning and remove this bias, which is we have too much popularity bias and so many algorithms, and we need to think about the long tail and be kind of more causal and unbiased. So we're looking at that.
Sounds good. I'm going to open up for questions. If you have a question, oh, I see a hand up there already. Could you please stand up, give us your name and where you're from?
Sure, it's Dave Friedel with Market Ally. I'm from US. I have a question about your causal relationship. When you remove the ability for the user to downvote or upvote a movie, what's the difference from that actually giving that user a personal experience that's going to be best for them, as opposed for best in Netflix interest in order to be able to be pushing more movie watch time, where I may not be getting a better experience for me, but you are getting more views for your staff to be able to say to an advertiser, look, this is getting so many hours of view play. Do you know what I mean? Like, I feel like maybe your causal is machine learning for your company as opposed to machine learning for the person.
So that's not quite fair, because we're trying to do causal machine learning in order to help benefit the users. At the end of the day, our goal is to increase how much people are watching and how they engage with the service and how much they're retaining at the end of the month, so they renew their subscription. Everything we do is really with that kind of North Star in mind. As far as downloads, I don't understand quite the exact engineering behind that system. But again, I'm pretty sure it's also helping as much as it can maximize how much the users are engaging with the service and how much they're retaining month to month. We always look at those that feedback from our users, and that completely informs what we try to accomplish with our product.
I think we have a question there.
Yeah, hi. This is Abhishek, and I'm research scientist with AWS. I have a question regarding contextual bandits. I've worked on it past also. So when you apply a context, so you have so many features and you explore number of permutations that you need to try. So how do you tackle this kind of a situation?
I mean, there's always a lot of additional machine learning techniques to reduce the dimensionality. When you're dealing with a bandit or a contextual bandit, you might have huge action spaces, many possibilities to action on. You might have a lot of differences in the users, but we do have ways of reducing the dimensionality. A little bit like what I described with that autoencoder and that deep learning, which learns to summarize the user in lower dimension. It's important to do these types of things, otherwise it's hard to generalize. If you can't say, how is this user kind of behaving like other users and kind of similar tastes?
I think we have time for one last question. Yes.
Hear me? Hi. Are the images, or will they ever be automatically generated?
So the images I was showing here are actually generated by creative teams, but we're now moving into a world where the creative teams get help from some automation. It's never going to be completely automated as well, as well as kind of some of the other systems I've described. But we are looking at ways of using computer vision and other automatic techniques as well to help find good imagery. Sounds
good. Any last burning questions? Oh, there are so many hands going up. Well, let's do one more.
Hi, I'm Saskia. I'm a data scientist by day and watch Netflix by night. So I was always wondering how you do this. Thank you very much. My question is, how do I get the best user experience? How do I make this algorithm work for me?
So at the end, we're trying to do, whenever we roll out something, an A/B test to make sure that most users are preferring this alternative experience. And there is kind of no better kind of gold standard than a statistically significant A/B test. When we look at half the users with the old experience and half with the new, we quickly figure out the ones with the new experience are watching more and are retaining better at the end of the month. And so that way we can get this overall improvement measurement. So I would say A/B testing is still the de facto standard there.
I think we're going to do a few more questions. I saw so many hands go up. I think over there, yeah?
So it's a common thing that multiple people use one Netflix account. Do you take this into account for your machine learning data science?
So it's true that sometimes multiple people will use the same account. Sometimes there's multiple people in the room watching on one account. You know, you watch with family and friends. It's not perfectly, let's say, there's no way to perfectly figure that out, but you can use some machine learning models that capture the fact that there could be multiple viewers and accommodate for that uncertainty. And so in our models, we try to have this kind of possibility with hidden, unobserved kind of possibilities of more than one person watching.
Sounds good. If you put your hand down, and I didn't see you before. If you have a question, please put it up again. There, we have one in the third row here.
Hi, I'm Ram, a data scientist. I have one question. You have this push and notifications to find how the user is seeing based on your recommendations or not. But how do you make sure I'm not seeing a paper ad or I'm not seeing some kind of internet ads for a movie recommendation I'm coming in? These might overlap with each other. How do you ensure, because of the email notification I'm coming in, this might not impact your casual learning effect?
So that's a good point. Maybe there's another reason why you watched that movie. It wasn't because we messaged you. What we're doing here is we're still capturing overall, kind of, with these models, the effect of the messaging. And with the randomization technique I showed you, actually still capture the causal effect of those messages. So you could have found out about that movie through a friend, or you could have found out about it through marketing, or because you saw a billboard on the street. But our models will actually capture the effect of the messages. The two-stage model, not the ordinary kind of classical model. But we do capture that effect, yeah.
Any last questions? And there you go. If
Hello.
you could stand up, it's hot.
Oh, yeah, sorry.
Thank you.
Yeah, I've been a bit sore throat, but I saw the graph with the contextual bandits. Oh, this echo, wow. There was also contextual bandits plus plus. I was wondering, what's that? Is there some source code somewhere, or?
Oh, so the contextual bandits plus plus is some extension that we developed internally beyond the usual algorithm. Again, we haven't published the details, but some kind of interesting improvement on the technique. So it's still not published and still kind of under the hood for now.
Sounds good. Well, thank you very much, Tony. It was a pleasure having you here.
Great, thank you, Surya.
And for those who missed it, Netflix is hiring, yeah? Well, thank you.